So what I want to do today is talk a little bit more about concurrency control. When we are done, I'm going to give a short break so that you have mental separation, and then we're going to talk about the second aspect of transaction management, which is durability. Okay? So concurrency control. Okay? So the thing that we talked about last time was that the whole point of concurrency control is to look at the kind of schedules produced. So you have this transaction manager sitting here. It is your, traffic lights. It tells you stop, go, right? So transactions all have to go through here to be able to do anything. And if a transaction is trying to do something that the manager doesn't allow, they are told to go into sleep. Go sleep until I can tell you to continue. And as a result of that, certain sequence of operations are possible, some are not. And what is produced is the schedule that this transaction manager allows. So one of the things we were saying was that this schedule, if you have the correct one, what you want is these schedules to be always serializable. So one thing we learned was that what if I implemented my transaction manager using two-phase locking? And the idea was that if you use two-phase locking in the transaction manager, then you can only get schedules that are serializable. So this is guaranteed to be. Because if it is not serializable, I can tell you that there is no way that they would be produced under strict two-phase locking. So two-phase locking, we generally just use 2PL here. So just to see how that works, let's try to see how, for example, one schedule may or may not happen. But this time I'm going to use the version we just started to talk at the end of last class, which was using two types of locks. A read lock, S, and an exclusive lock, or write lock, X. So the idea is that, only one transaction can have a lock X and no other types of lock, whereas multiple transactions can read everything, can read it at the same time. So if you're using two types of locks, okay, so the first thing we talked about was, for example, is this schedule possible? So technically, you should allow a transaction to read and write something and commit, right? So if I use the two-phase locking in basically as it is, what that would mean is that transaction 1 has to lock 1 with shared lock before it can read. Then, for this to happen, it actually has to release the shared lock and then get an exclusive lock so that it can write. But under the two-phase lock, you cannot release a lock and get a new lock. Not possible, right? So you cannot do this. So because of this, we are going to introduce a loophole. We are going to say that if nobody else is holding a lock on this item other than you, so you have either there is no lock, or the only person that is locking it with a shared lock is you, in that case, you can upgrade your lock. So this will mean that you don't actually have to release the lock. You can actually upgrade it. So what you can do is upgrade the lock to an X. without releasing the shared lock. So just change it from shared to exclusive. Then you can do write X, and then you can commit. So this schedule is possible under this rule. Okay. So let's try to see a different one. Let's say I have read 1 of X, read 2 of X, write 1 of X, then commit 1, and well, let's do this. So can I do this, for example? Is this possible? So, well, I will have to lock this with shared lock. Then for this to happen, transaction 2 has to lock with shared. Then for this to happen, transaction 2 has to actually release the lock, so that only transaction 1 is holding a lock. So transaction 1 is going to release the shared lock, at which point transaction 1 can upgrade the lock, and it can continue and commit. So this schedule is possible, right? Are you with me so far? Right? So it's possible because I can tell you if the lock and unlock occurred in this order. It is not against two-phase locking, so this schedule can happen. Can this schedule happen if I only had a single type of lock? If I had only one lock? No. Why can't this not happen? Because if I only had a single lock, then I have to lock it here, then I have to unlock it here, so that this can happen, right? If I unlock it here, it cannot lock it again. So this cannot happen if you use a single type of lock, but it can happen with two types of locks, right? So this is possible. With two types of locks, but not a single lock. And this is exactly why we have introduced two types of locks, because this is still a serializable schedule, right? So if you look at the conflict graph, what are all the conflicts here? What are all the conflicts in this schedule? R2 of x, write 1 of x. Like this, right? So that means this schedule is serializable because it has no cycle. And I would not be allowing it if I was using a single lock, but with two locks I can allow it. So the whole point of two locks is to have more schedules that are possible, so I can have more concurrency, but still not cause any problem because you can still show that this guarantees serializability. Okay? So let's try and see a slightly different one. Let's say I have the following. Is this schedule possible under two-phase locking with two types of locks? Think for a second. How many of you say possible? 1, 2, 3, 4. Okay, there's some. How many say not possible? All right. Let's see. So what I can do is I'm going to lock it with shared here. then I'm going to lock again with shared here. And let's say transaction 2 at this point was going to write y. So it actually asked for an exclusive lock on y. And it can get it because nobody else is using y. And then, since now transaction 2 has everything it needs, it also released the lock on x. And at which point it stopped operating because, let's say, the CPU gave more time to transaction 1 now. Now transaction 1 comes and it's the only one holding a lock, so it can upgrade its lock to exclusive. And this can happen because now transaction 1 is holding an exclusive lock. This can happen because transaction 2 has already locked y up here. And it locked it before it released the lock, so that's allowed under two-phase locking. So now this can happen, right? So this is allowed under two-phase locking. Okay. Yes.
So when you're reading one of the first transaction and you read two, but when you close the lock on transaction 2, right? Because you're writing with transaction 1.
Yep.
Doesn't that mean you wouldn't be able to open up another lock or why?
But the point is that as soon as transaction 2 releases a lock, it cannot get a new lock, right? But it is possible that it got the lock before it released the lock, right? So the idea is that, transaction 2 got the lock, so now transaction 2 had everything it needed, right? So it can now release a lock it doesn't need anymore. As long as it happens in that order, it's good, right? But I don't want to allow you to get the lock to release a lock, right? So under two-phase locking, this is still possible, right? But what is not possible is this, right? So this is possible. And this is still serializable because, again, the only conflict is R2 of x to W1 of x, right? So this is still the same transaction. So this is still this because of R2 of x and W1 of x is the only conflict. So this is still true, okay? Now let's try this, okay? So R1 of x, R2 of x, W1 of x, W2 of x, right? This ought not be possible because this one is a cycle, right? This one is not serializable. So let's see how is that possible? Well, for this to have happened, you have to have locked it here. Then this has locked it here. Now at this point, right, for this to happen, for sure T2 has unlocked it. This is the R. And T2 and T1 has upgraded it to an X. So at this point, for sure, what I know is that T2 has released the lock. So it's in shrinking mode. And T2 has no lock on X. Okay? So T2 has no lock on X because for sure it has released it. And it is in shrinking mode. That means it cannot get another lock on X. So we know for sure that it cannot get a new lock. So because of that, while this can happen, this cannot happen, right? Because I can no longer write X, so this cannot happen. So this schedule is not possible under. So this schedule is not possible. So all that I'm trying to say is that if you use two types of locks, you allow many other different schedules. Than you would get in a single lock, but you still have serializability. So, lock with the weakest possible lock so that you can still do lots of things, but make sure that nothing bad can happen. This is really the whole point of concurrency control. So you can see that, after you've come up with this idea, what people have started to do is to find, can I change my lock types to include even more other types of locks so that you can actually do more things. So that led to different levels of locks. So just so that, for example, you know a little bit about this, that there are other schemes for locking. So for example, you can have multiple granularity of lock. This is used a lot in indices, right? So you have an index, right? So let's say that you are going to insert a node into the index. So you're going to change this page, right? So if you're going to update this leaf node, technically you want to lock this node, right? But what happens up here? If you lock this with an X, that means until you finish updating that one leaf node, nobody can access the whole index, right? So which is actually not very good, because in all likelihood you're going to change that one page. It's not even going to affect anything else, right? So because of that, what you do is you basically have multiple granularity. So basically, you have in the higher level of the index intention locks. It's like the mother and father asking, what is your intention to my index? So are you going to be reading my index or writing or doing some combination of both? That's what you write at the root node. So instead of saying that I am going to lock this whole index, I'm going to say I'm going to change something below. So this is my intention to change something below the root node, right? So IX just means intention to change a node below. So an insert operation is an intention to change the upper level, and then whatever root node you change, the leaf node you change, you're going to lock that with an X, right? So, for example, if you have an insert, you're going to use IX for upper level, and X for leaf node being changed. The other thing is that if you're just reading, then you're going to lock the root node and internal nodes with an IS. So that means intention to read. So you're going to basically, if you're going to read a certain node from the index, then you basically lock the root with an IS, and then the leaves with just S. So if you're doing an index scan, you're going to scan all the nodes. In that case, you're going to probably lock the root node with a S because you're reading everything. Whereas IS means that I'm only reading a single node. So intention to read a node below. So, read x equals 5, then IS for root, and S for node being read. So the intention locks basically allow you to do this in such a way that you can have the following. So suppose if you had two transactions changing different leaf nodes, this is possible because you can have two IX locks as long as the node that you are going to lock for an X is different, right? So you can have two IX locks and X on different nodes. So basically, you will see lots of schemes where you change the kind of lock you have so that you can allow more transactions to go in. It happens that intention locks are actually quite useful because if you lock the index, then you can lock the index on a condition. So let's say that you want to lock, index on x equals 5. Okay. All you have to do is lock the node with x equals 5, and that means any node below will also be locked, right? So this is important because sometimes when you are, let's say, querying x equals 5, you don't want people to insert new tuples with x equals 5 because you want to count how many tuples with x equals 5 you can lock on that condition. So true serializability requires that whatever condition you are searching on cannot be changed, the tuples that satisfy it, which actually the index will allow. So this is the general idea of, this is what I forgot, is to close the syncing, all right. I don't have the compatibility here, all right. So this is kind of the general idea of compatibility. Trying to remember if I can remember all the compatibility matrix. But one thing that we can say is that if you do have locks, what is the most common problem that they generate? Deadlocks. Okay. So the idea is that if you're using locks for concurrency control, then when you lock an item, two transactions can just basically be waiting for each other infinitely. So let's say I have transaction 1, transaction 2. Okay. So this one reads 1x. So for this to happen, it gets a shared lock on x. And this one decides to read y. To do that, it gets a shared lock on y. Now let's say T1 decides that it needs to actually write 1, right? So it requests x lock. So it wants to write y. So it requests a lock, bless you, lock on y. But it cannot get an exclusive lock on y because transaction 2 is already looking at this. So then we suspend T1. T1 cannot go on until this lock is released, right? So basically all this means is that T1 is waiting for T2 to release lock on y. Okay. So T1 is suspended. Now T2 is going to decide that it actually wants to write x. So it requests a lock on x. And it cannot get it because T1 is actually still holding the lock, right? So when you suspend, you're not releasing the locks. So as a result, I'm going to suspend T1, suspend T2 until this lock is available. So what that means is T2 is now waiting for T1 to release lock on X. Right? So T1 is waiting for T2, T2 is waiting for T1. Since none of them is doing anything, nothing can go forward, right? So as a result, T1 and T2 can never resolve this conflict, sadly. So this is a deadlock, right? So if you look at who's waiting for who, they are waiting in an endless cycle, right? T1 is waiting for T2, T2 is waiting for T1. So any system where you use locks, inevitable that it can cause deadlocks. So as a result, you actually have to do something about this. So you can do various things. So what to do in terms of deadlocks? Well, what you can do is you can detect them by periodically checking the wait for graph. Okay. If there's a cycle, that means you have to break the cycle. You have to break the cycle by choosing one of the transactions and aborting it. So when you abort the transaction, you're going to undo everything that it has done. You're going to roll back. So basically, if there's a deadlock, choose a transaction and abort and roll back all changes. If that does not solve your deadlock, if you are highly deadlocked, then choose the next one until you no longer have a deadlock. So which transaction to use to actually break a deadlock? Well, it will totally depend on what your application is. If you have an application that has very long running process, right? So the problem is that the long running processes, like something that is going through every single person and updating something, right? Like, for example, suppose this was the CAP report running, right? You assume the CAP report takes some time, right? And as it is changing lots of things, if you abort that transaction, you're going to also have to abort many, many changes that it has made, and then you're going to restart and do the whole thing. So that transaction has consumed so much of your processing power, maybe you want to let it finish whatever it's doing, right? So, but there may be cases where if a transaction is holding so many locks that everybody else has to be aborted, maybe you want to actually abort that one, right? So you can have different algorithms here. It could be longest running. It could be the shortest running. It could be the one with the most locks. You can have many different methods. You can also have a mechanism to avoid deadlocks. How would you avoid deadlocks? Well, you can say, for example, give every transaction a timestamp, and you can never lock something if a transaction with a smaller smaller timestamp is holding a lock on that item, right? So you never wait for somebody who's older than you, right, or younger than you. It's your choice. So if you never wait for old people, right? So that means as soon as you see somebody is holding, say, oh my God, they're gonna take forever. There's like this long Sedaris routine about this old couple buying coffee and just having this long conversation, and you're just like, oh my God, give me my coffee. So if you never wait for another older transaction, as soon as you need that lock that somebody older is holding, you just abort that transaction. So this way you can never have deadlocks. But you're going to have more aborts, and then you're going to basically have many restarts. So you're going to have less concurrency, but you will never have to check for deadlocks. So you can have timestamp for each transaction. And not wait for a lock if, let's say, an older transaction, older or newer, depends on how you want to implement it, transaction is holding a lock on that item. Okay. So it happens that timestamps are very useful for many other things. So giving a timestamp of when the transaction starts, as long as you have a database where the timestamps can be uniquely identified, right? So if you have a distributed system, how many of you took Stacy's class? All right, so you know something about distributed systems, right? Your biggest problem is synchronizing the clocks, right? Otherwise, timestamps will not work in any distributed system, right? So this was Google's main achievement, to figure out how to solve that problem, right? So timestamps are great, but you have to make sure your clocks are synchronized, which is actually one of the reasons one of our programs kept failing out. So this is an important problem. But once you have good timestamps, you can do a lot of things. It turns out you can actually implement a mechanism that doesn't use locks at all, right? It will take me a while to explain what that is like, but I will try to explain it quickly. But it is pretty cool, so I will just give a short overview of it. Okay, so you can use something called multi-version concurrency control, okay, or Mvcc. So each transaction has a timestamp. Okay, so this is important. Once I have a reliable timestamp, I am going to basically be very permissive. I'm not going to lock anything. I'm going to assume that at the time you start your transaction, the database of everything that was committed at that time is stuff you can read, right? So this is, you're always making sure you're reading committed information. So the idea is that, so let's say this is the database, okay? As soon as your transaction starts, so T1 starts here, you create a copy of this. Not actually, but let's say you do, right? Okay, and T1 is operating on this copy, so T1 make changes to this. And creates its own version of the database. Okay. It could be that later on here, T2 starts. Okay. Now, if T1 hasn't committed here, it's the same database, but now I have a different copy. Let's call this DB star. And T2 makes changes to DB star. Okay. So basically, multiple versions of this database are existing. But obviously, you are not making a copy of the whole database. You only care about the copy of things you change, right? But I'm going to keep multiple copies of the same data item. Now, the thing that's going to matter is, and the thing is that since you are kind of allowed to read anything, I'm going to read the version of X. Let's say if I'm going to read X, I'm going to read the version of X that was committed before I started. And that's always a committed version. And when I'm trying to commit here, I'm going to make a decision. So for example, if I realize that my commits not conflicting with anybody so far, I can make those versions the last version, and I'm done. If my commits actually conflict with somebody who came before me, somebody actually beat me to it, and if that was a transaction that started after me and finished first, wrote their changes and done, right? So the last version of the value of x that was written is actually a value that existed after me. In that case, I cannot really go on. I'm going to abort, right? So basically, in the multi-version control, you allow multiple transactions to go at the same time. And at commit time, you either commit those changes, then that version becomes the last version, or you abort the transaction altogether. So you proceed under the assumption that everything is good until something bad happens, right? So I can try to explain this, but how many of you have seen, maybe not as many times as I have, Back to the Future, right? 2, where he draws the line of different timelines, right? Actually, I have a video, I'll show it to you. So this is exactly what's happening. Multi-version control is kind of creating alternate realities, but then at the time you try to commit, you actually check to see if that actually causes a problem. If you touch things that nobody has touched, there's no problem. You can commit, that version becomes the latest version. But you actually keep track of the older versions because other transactions may still be reading them. If somebody has changed it after you, then you have to abort your transaction. So this is the general idea of version control. I can actually